An expansion device is a critical component in a refrigeration system that controls the flow of refrigerant into the evaporator while reducing its pressure and temperature. By doing so, an expansion device helps achieve the desired cooling effect. There are several types of expansion devices, each designed for specific applications and system requirements. Below is a description of the most common types of expansion devices used in refrigeration systems. A hand expansion valve is a type of expansion device used in refrigeration systems to manually control the flow of refrigerant into the evaporator. Unlike automatic or electronic expansion devices, a hand expansion device requires manual adjustment by an operator to regulate the amount of refrigerant entering the evaporator, making it a simple and cost-effective option for systems where constant supervision is available or load conditions are stable. Hand expansion valves are often installed downstream of a solenoid valve that is interlocked with an operating level float switch or a temperature probe. The solenoid valve provides automation to what otherwise would require continual oversight. The advantage of a hand expansion valve is its simplicity and low cost. The drawback of a hand expansion valve is that it cannot be directly automated, and there is a risk of over or underfeeding an evaporator if the valve is not set correctly. A capillary tube is a simple fixed orifice expansion device consisting of a long, narrow tube with a small diameter. It is a non-adjustable passive device that controls refrigerant flow based on system pressure differences. As the high-pressure liquid refrigerant enters the capillary tube, its pressure drops due to the friction along the length of the narrow tube. This pressure drop causes the refrigerant to expand, cool, and partially vaporize before entering the evaporator. Capillary tubes are inexpensive, simple, and require no maintenance. However, their fixed design does not allow for adjustment for fluctuating loads, so their application is limited to small refrigerators, water coolers, and window air conditioners. An electronic or motorized expansion valve is a highly precise, adjustable valve that uses an electronic control system to regulate refrigerant flow into the evaporator. It offers superior control over refrigerant flow compared to mechanical expansion devices. Sensors placed throughout our refrigeration system feed real-time data such as temperature, pressure, superheat, or liquid level to the electronic controller. Based on this data, the controller adjusts the valve stepper motor to open or close the valve, maintaining optimal refrigerant flow. Electronic expansion valves provide maximum efficiency and better system performance since they allow real-time adjustments over a wide range of operating conditions. The downside of this type of expansion device is the cost and increased system complexity. An orifice expansion device, which is sometimes called a piston orifice or fixed orifice expansion device, is a simple non-adjustable expansion device used in refrigeration and air conditioning systems to regulate the flow of refrigerant into the evaporator. This device operates by forcing the high-pressure liquid refrigerant through a small fixed opening called an orifice, which causes a pressure drop, resulting in partial vaporization and cooling of the refrigerant before it enters the evaporator. The orifice expansion device is commonly found in smaller, low-cost systems due to its simplicity and reliability. The downside of orifice expansion devices is that they cannot adjust to changing load conditions, and they are susceptible to clogging, which can be mitigated by installing a strainer upstream of the device. An automatic expansion valve is a pressure-sensing device that maintains a constant pressure within the evaporator by adjusting the flow of refrigerant based on the evaporator's pressure. As the pressure in the evaporator drops, the diaphragm detects this change and opens the valve to allow more refrigerant into the evaporator. If the evaporator pressure increases, the valve closes slightly to reduce refrigerant flow. Automatic expansion valves are simple and inexpensive to install. Unfortunately, they are not ideal for systems with varying load conditions, since they do not respond to changes in superheat, which may lead to inefficient performance in some scenarios. A thermostatic expansion valve, or TXV, is one of the most widely used expansion devices in refrigeration and air conditioning systems. It regulates the flow of refrigerant into the evaporator by sensing the superheat at the evaporator outlet. Remember, superheat is the difference between the refrigerant's temperature and its saturation temperature. The key components of a TXV are the sensing bulb, diaphragm, and spring mechanism. As the refrigerant leaves the evaporator, the sensing bulb detects superheat. The sensing bulb contains a small amount of refrigerant which increases in temperature and pressure as superheat increases. The sensing bulb connects to the diaphragm, which when exposed to higher pressures affects the spring mechanism, causing the valve to open and allow more refrigerant flow. Supplying more refrigerant to the evaporator will reduce the superheat and cause the reverse process. Since the refrigerant flows through the evaporator continuously, a TXV provides real-time flow adjustment.
All right, what I've got drawn here on the whiteboard here, it's kind of a cutaway of a thermostatic expansion valve, often called a TXV, okay? And this is a type of expansion valve widely used in refrigeration systems, especially historically, but a lot of higher temperature applications, commercial systems, and so forth. And so first, just a little bit of naming conventions, what things are called. We've got the cutaway of our valve here, and then this tube here that's connected down here to this bulb with the pink inside. That's a capillary tube, and that bulb is full of a little bit of refrigerant, okay, which changes temperature depending on the superheat in the suction pipe. So this is providing a pressure, that bulb pressure, what I've written as P bulb, pressure on this next component, that straight line, that's representing the diaphragm of the valve. So it's providing a pressure on that diaphragm, which is connected to the valve mechanism, which allows it to open and allow more refrigerant flow, or close and have less flow, which is also connected to a spring. And that spring, of course, has a constant, which is tending to cause that to close. Okay, the spring is wanting to force the valve closed, and it can be adjusted with that little screw that I've drawn in here. So liquid refrigerant enters here through the pink solid line, enters the valve. Okay, and right now, kind of as it's displayed, is showing it as closed, so it wouldn't be able to go too far. Maybe just a little bit of refrigerant is passing through the valve and now entering the evaporator here, okay? And then exiting here a suction pipe, which is where the bulb is connected to. Now connected, but in a fully independent circuit, okay? So as our superheat increases, because let's say we're not getting enough refrigerant flow, so the temperature at the outlet of the evaporator will increase, because whatever refrigerant is in the evaporator will evaporate, and that will then, any additional heat will cause the temperature to rise, become superheated. Well, that will increase the temperature and pressure in this bulb, which connected to the capillary tube, will therefore increase the pressure on our diaphragm, right? And that's gonna cause this to begin to push down. And you can kind of visualize what's gonna happen as this pushes down. As this pushes down, it's gonna allow more flow. So now we get more liquid flow. More liquid flow is gonna equal less superheat. Okay, less superheat then will cause the pressure inside our bulb to decrease, right? Which is connected to our diaphragm. That's causing that pressure decrease. The diaphragm will start to go up a little bit, and therefore our valve will close, causing there to be less liquid flow. So the TXV is kind of constantly just tracking with the system and self-adjusting in that way. All right. So that's the basic explanation of how it works. If you look at here, we have three pressures we're talking about. We've mentioned the bulb pressure, we've mentioned the spring pressure, but there's also the evaporator pressure. So we know that the pressure inside the bulb here has to be equal to the spring pressure plus whatever the evaporator pressure is, right? The evaporator has a pressure, more than likely a pressure that's, if it's it could be greater than zero, a positive pressure, it could be less than zero in a really cold application, but either way, those have to equalize. So that's the way a TXV works.